Okay, welcome to the fifth installment of the Functions as Series video series. Today's topic is the alternating series error bound. And let's jump in. We've been looking at the natural log of 2 as a power series. And as a quick review, we started out with wondering what is the natural log of 2. We expressed it as a function of e, and we realized that e and natural log are quite complex when you're actually trying to calculate things. And so instead of worrying about this limit, we expressed natural log as a power series using the geometric series, and then we took the antiderivative. And knowing now we have a series for natural log, we can plug in 1 for x because 1 is included in the boundary of the interval of convergence. So plugging in that 1, we end up getting that natural log 2 is the alternating harmonic series. And so this is a little more pleasant to look at than maybe the definition of E with this K here. And although they're both infinite series in nature, this one's a little more aesthetically pleasing and possibly easier to work with. So then this begs the question of, is our new series actually a good series? Meaning, can I, with a reasonable number of terms, let's say 10, can I use 10 terms to get a reasonable approximation for the natural log 2? And after a series of calculator explorations in the previous videos, we saw that this is actually a terrible series to approximate the natural log 2. Meaning, if I were to store this in my calculator as Sn and look at maybe the 5th, 10th, 25th, and 50th partial sums, meaning I go all the way out to 50 terms and add them up, how close is this decimal to the natural log? Well, using some more calculator mechanics, we set the error function to be the distance between the natural log of 2 and my xth partial sum. So you'll notice here if I plug in an x, well, that is the x, and the sum from 1 to x is x terms added together. So if I were to go x terms out, what is the error to the actual value of natural log 2? And if we were to go 10,000 terms out, the 10,000th partial sum, we would have an error of this, which is not very accurate. We're not even to 6 or 7 decimal places of accuracy, and we've used a lot of computational power. So we say that this is not a very good series for approximating, but nonetheless, we want to ask some more follow-up questions. We say, if you did want this much accuracy, what is the smallest number of terms you would have to use? Well, if we just did some guess and check, we would arrive that the 5,000th partial sum has this much error, while the 4,999th partial sum has this much error. Well, this is too much error given the restraint, so we know that 5,000 terms is the first time we get the desired error margin. So this is quite an easy thing to do with the calculator. It's just guess and check. But of course, we don't always have access to technology. And the question comes to, if you do not have a calculator, what is the most accurate that you could guess as the number of terms required? And that's where the alternating series error bound comes in. So before we dive into the formula, I'm going to build the intuition for it. And it starts out with looking at the difference between the subsequent partial sums. So if we were to look at the second partial sum, that is adding the first 2 terms together. And I looked at, instead of that, the first partial sum, which is just adding the first term together, what is the difference between these 2 series? Well, I take S2 minus S1, subtract this list from this list, and we're left with only the negative 1/2. That's the second term in S2. Similarly, if I were to go to the 6th partial sum, and I were to subtract the previous partial sum, so the 6th sum minus the 5th sum, well, everything in the list cancels, leaving only the 6th term. So the 6th sum minus the 5th sum leaves only the 6th term. And so in generality, we say if we subtract the nth sum minus the previous sum, well, we're only left with the last term in this series. So keep this thing in mind as we move into the next frame. We're going to do it visually now. So here, this is 1. if I subtract 1/2, that's S2. So S2 is equal to 1 minus 1/2. S3 is going to be equal to 1 minus 1/2 plus 1/3, minus 1/4 plus 1/5 minus 1/6, dot, dot, dot. So what we're seeing is that if I wanted to go from S1 to S2, what I'm doing is I'm adding the second term, which is a negative 1/2. If I want to go from S2 to S3, what I'm doing is I'm adding the third term, which is a positive 1/3. And so you end up getting this concept where you're oscillating below and above and below and above the actual value of natural log 2. And at the same time, we know that each term is getting smaller. So this is a 1/2 distance, while this is a 1/3 distance, this is a 1/4 distance, and this is a 1/5 distance. So while we're oscillating between above and below the natural log of 2, we're also getting closer and closer, hence the idea of convergence. So now, what are we actually looking for? What I'm asking is, how close is the first partial sum, the value of 1, how close is that to the natural log of 2? Well, this is what we're going to call error, the error between natural log 2 and my first partial sum. What this red line represents is the distance between S2 and S1. How far is it from S2 to S1? Well, S2 minus S1, remember, is A2. And what we see here is that the error from S1 to natural log 2 is a smaller distance than that of S1 to S2, which is A2. So putting that step together, we know that the error between S1 and natural log 2 is less than A2. Okay, let's do it again. We're going to do 3 of these just to really hone in on a pattern. In this case, the fourth partial sum's error to natural log 2 is definitely smaller than this red line. And the red line represents the distance between the fourth and fifth partial sum. The distance from the fourth to fifth partial sum is A5. So again, we have that the fourth partial sum's error is less than A5. And lastly, we do the same argument again for the seventh partial sum. The seventh partial sum's error is smaller than the distance between S7 and S8, because the distance from S7 to S8 is A8, so A8 is definitely larger than the error from S7 to natural log 2. So if we were to put these 3 steps together, what we're seeing is that the nth partial sum is always an error less than the next term in this series. So the fourth partial sum error is less than A5, while the seventh partial sum's error is less than A8. And that gives us a really nice formula moving forward. We see here the general idea for the alternating series error bound. The nth partial sum's error is less than the next term in the series. And that's very clear visually. So now let's actually use it to calculate the same question we did before. We want the natural log 2, which we found as the alternating harmonic series. And our question is, what is the smallest integer m where the error to natural log 2 is less than 0.0001? Well, if this is the nth partial sum, the error is less than the next term. So we plug in m plus 1 in for k, m plus 1 and m plus 1 here. And we want that error to be less than 0.0001. Well, negative 1 to any power with an absolute value is going to be 1, while m plus 2 stays in the denominator. And these are both positive quantities. So we multiply through and we show that m must be greater than 9,998. And since m is an integer, 9,999 is the smallest integer. Now keep in mind, when we did this investigation with the calculator, we got 5,000. But without the concept of the calculator and the computational power, we're left to other error-bound tests. And by doing it by hand, this is about as good as we can get. There are other error-bound tests, but the alternating series error-bound is as straightforward and simple as it gets. So what we're looking at is by hand a much larger number than what we could have found by calculator. But that's fine. So moving forward, we have two practice problems. The question is, if we know the series for pi, which we found in a prior video, is the alternating values over the odd numbers. What you want to do is see what is the smallest integer m where you can get this much error. Similarly, in part B, there's a very beautiful series for pi squared over 6, and we will be proving this in a future video. Well, we owe this proof thanks to Euler, one of the greatest mathematicians, and so I'm excited to walk through that just in a future video when we finally get a series for sines and cosines. So look for that in the future. For now, work on this alternating series, error bound, and we'll come to this back in a later video. Okay, so pause the video, take some time to work this out on your own, and then on the next slide I'll be going through the solutions. Okay, solution. We are looking for a certain error. Go ahead and remove that parentheses, that's a typo. And then the mth partial sum error will be less than the next term in the series. So we plug an m plus 1 in to the value of I here. And negative 1 to any power inside of absolute value is just going to be 1. And this simplifies to 2m plus 1. These are both positive quantities, so we multiply through, and m must be an integer larger than this, so we get 5,000. Pretty straightforward. The alternating series error bound is a very nice, beautiful formula. So using this now exciting series for pi squared over 6, we see that the pth partial sum's error should be less than the next term. We plug in a p plus 1. Well, do some algebra simplification. We multiply through the 10,000, and we get p squared must be p plus 1 squared greater than 10,000, so m must be greater than 99, meaning 100. Now what you'll notice is there's a huge difference between the previous solution, which took a lot of terms, while this one only takes 100 terms. So we would say that this series converges to pi squared over 6 quite quickly. We very quickly get a very accurate number, assuming 0.0001 is accurate, right? That depends on your error margin. Okay, so this is the conclusion to part 5. I will be looking for part 6 in a video soon where we'll be beginning to look at more series that are derived than just things of geometric nature. So we're looking at sine, cosine, e to the x. And this is going to be an exciting jump forward in our eventual proof of this series here. Okay, thank you for watching, and I'll see you in the next video.